Let's just recall the Laurent theorem, which states that if a function f of z is analytic in a ring region like this, then it can be represented in the following way. And z0 is some center in this ring region, and we say that this Laurent series is developed around z0. We also know that these coefficients can be written as these integrals. These integrals are often difficult to find, so we'll show you an example where we can find these coefficients without computing the integrals. So let's go to this example. F of z is equal to this fraction, and we say that z0 is equal to 0. In this case, the function, this function f of z is analytic everywhere except at z equal to 0, where we get some 0 in the denominator, and we also get some problem when z is equal to -1. Then we obtain 0 in the denominator. So we have two problems. So for example, we know that the function is analytic inside the circle with radius equal to 1 and center at 0. So let's try to find the Laurent series in this region around this point, z0 equal to 0. Before starting the process, we always write down the general expression for the Laurent series. And this is a general expression, and in our case we have that z0 is equal to 0. So just put 0 into this, replace this z0 by 0, and we then obtain this more easy series. And we can write some terms. We write out some terms starting with n equal to 1. We obtain the first term b1 times z to the power of -1. This term, we continue with n equal to 2, then we get b2 times z to the power of -2, this term, and so on. We continue this infinitely many times. This series we can obtain in the same way. We have the first term is just a0 times z to the power of 0, but z to the power of 0 can be replaced by 1, and then the first term is just a0. Next term is a1 times z to the power of 1, and the third term is a2 times z to the power of 2, and so on. So this is correspond to this series, and this is correspond to this series, and we usually call this the principal part of the Laurent series. Well, now we see that we can replace this denominator by just placing z to the power of 3 here and multiply it with 1 plus z square. Then we obtain the same as above. Now I'm doing a little bit trick again, because I want to reduce the size of the polynomial on the numerator, and therefore I do as follows. I split this numerator in two terms. one term which is exactly the same as this factor, 1 plus z square, and we then miss z square in order to obtain 1 plus 2 z square. And the reason for doing this is that I now obtain, I can split this into two terms, one term like this and the other term like this, and then I can just make the following simplification. I can remove these two factors, and therefore I obtain 1 over z to the power of 3 plus, and here I can remove z square in the numerator and denominator, and I obtain this. Well, now you see that we are very close to see a limit of a geometric series in this part, because this is just equal to 1 over z times 1 over 1 minus z square. This is just a trick I'm doing when I have plus here. I want it to be minus, because then this is just the sum of a geometric series with u equal to minus z square. We have done this before, and we know that this limit corresponds to the geometric series minus z square, this guy, to the power of n, and we are counting from n equal to 0, n equal to 0 to infinity. And of course this is equal to this, so I must multiply with 1 over z here. And 1 over z is just the same as z to the power of minus 1. And I can multiply this with each of the terms in this series, and then I obtain, when I replace minus by just minus 1, then I obtain minus 1 to the power of n times z to the power of 2n minus 1. And of course I can write this as z to the power of minus 3. Let's take a look at the convergence of this geometric sequence, because we know that a geometric sequence, we would call this u, converges when the absolute value of u is less than 1. So we must assume that this guy is less than 1. And this is the same as saying that the absolute value of z to the power of 2 is less than 1. So the absolute value of z must therefore be equal to the square root of 1, which is only 1. Note that we also should have that this set is larger than 0, because otherwise we obtain some problems here. Set to the power of minus 3 goes to infinity when set goes to 0, so it's not analytic at this point. Let's just see some terms, the first terms of this series. We see that minus 3, set to the power of minus 3, is some term in the principal part of the Laurent series. And I'm writing down some terms of this infinite series, and I'm starting with n equal to 0. Then I obtain minus 1 to the power of 0 times z to the power of 2 times 0 minus 1. Plus, then I take the next term, which appears when n is equal to 1. Minus 1 to the power of 1 times z to the power of 2 times 1 minus 1, and so on. I continue this, and we see that well, here the coefficient of z to the power of minus 3 is just 1. The coefficient in the term corresponding to n equal to minus 2 is 0, of course, because we do not have any terms in this series which is a product of some number and z to the power of minus 2. On the other hand, we see that this term appears here. We have minus 1 to the power of 0 is just 1, so here is the coefficient, and this should be multiplied with z to the power of minus 1. So here we have all the terms in the principal part of the Laurent series. And continuing this, we obtain that this series, the rest of this series, is just equal to 0. This is just the first term in let me show you this term A0, which must be equal to 0 because we don't find any constant value here, so it must be equal to 0. Then next we obtain this term, which is just z to the power of 2 minus 1, which is equal to 1, so it's just z. So here we have this A1 coefficient. This is A2 coefficient because there are no terms in this expression where we have z to the power of 2. But we have here a term z to the power of 3, because here we have 2 times 2 minus 1. So this is this term. So now we are able to identify all the coefficients in the Laurent series, all these an coefficients and bn coefficients which are here. Here is the so-called principal part.